So iCE40 Ultra Plus product features, I believe the block diagram that's shown on the screen describes every major block in the device. As far as the features are concerned, the static power consumption of this device is targeted to be less than 100 microamps. 1 megabyte of on-chip low-power SRAM, and a dimension on the package of smaller than 2.15 millimeters by 2.55 millimeters, and 128K bits of block RAM, and up to 5,280K LUTs of user logic, and 8 multiplier accumulator DSP blocks, fully functional DSP blocks, and 2 low power 10 kilohertz and high frequency 48 megahertz oscillators, as well as 2 iCE40 blocks and 2 SPI blocks for peripheral interfaces, and the non-volatile configuration memory to program the device and boot the device from when that function is required, the non-volatile function is required. So this device is comprised of all these blocks, and the non-volatile functionality can be bypassed through programming the SRAM configuration of the device. So the device has an SRAM based architecture where the function and the configuration is booted up from SRAM. However, upon power up, if the NVCM memory is populated with a configuration, we allow that configuration to be self-downloaded into the device. So multiple ways of bringing up this device. So here's a quick block diagram of the product features. So the technical details of iCE40 Ultra Plus family are as follows. The block diagram shows all the major components of the device. As far as the logic is concerned, we do have a 4-input lookup table logic block. 8 of these comprise a logic cell, where we call the programmable logic block, PLB. And there is carry logic in between each one, and a flip-flop per lookup table is available with enable and reset controls. The block also contains embedded block RAM, and these are 4K bit DP RAM modules, dual port RAMs, and there is for every device density there is a different number of block RAM available. At the last page of this presentation there will be a list of all the available resources. There is 2 iCE40 hard blocks and 2 SPI hard blocks in this device. These are standard iCE40 and SPI blocks where the logic of these are in hard format inside the FPGA, and the user, all they need to do is to instantiate these blocks and make use of them in their logic. The device is comprised of 8 DSP blocks, and these are full functional DSP blocks. There will be a slide later on showing the details of the DSP blocks. There is a power control module in order to control the power consumption of the device, putting the device in a sleep mode or reducing the power of certain sections of the device. There are various I/O banks available in this device, and as a matter of fact, there's 3 I/O banks available, banks 1, 2, and 0. Each one of these banks can be connected through an external VCC I/O pin to a voltage between 1.8 to 3.3 volts. So each band can operate at a different voltage. Hence, the IOs can be hooked up to those type of interfaces. One major difference of this device family with the previous variations of this device family is ULTRAPLUS contains 4 256K bit SRAM blocks. That builds a 1 megabit of SRAM available in this device for various functionalities such as buffering of video, sensor buffering, and so on. So this particular device family, a variation of iCE40 devices, lands itself very nicely with applications where a lot of memory is required, buffering is required. The device also has a couple of oscillators, a 10 kilohertz oscillator and a 48 megahertz high-speed oscillator. These oscillators can be turned on and turned off as a bit stream is built. So the only time that these oscillators are not recommended to be used are when the application requires an extremely low power. Oscillators do increase the power consumption of the device. There is a PLL in the device, and each one of these devices can have I/O pins, clock I/O pins connecting to the PLL, generating various frequencies, or the internal oscillators can be hooked up to the PLL, generating different frequencies. And the PLL can also be used to clock external devices. So the outputs of the PLLs can go to I/O pins for external use. There is some delay lines available in the device, 50 nanosecond delay lines and filtered delay lines. And there is a configuration memory, a non-volatile configuration memory available in the device called NVCM. This is a one-time programmable configuration memory where if programmed, it is not a reversible or reprogrammable function. So you can always make sure that your code is 100% before programming the NVCM. Otherwise, the function of that memory becomes unusable. Now, that memory can be bypassed by the external programming interface. There is a slave SPI or a master SPI interface to program the device. So even if the NVCM is programmed, the external programming interfaces can reprogram the device, the SRAM configuration portion of the device. And so an external processor or a different device can come in and reconfigure this FPGA. There is a slide later on that shows the details of that as well. So as far as the DSP blocks are concerned, they are configurable blocks, 8 of them total available in each iCE40 devices. There is a configuration where you could have 2 8x8 multipliers and 2 16-bit accumulators in one DSP block, or those can be combined to build a 16x16 multiplier and a 32-bit accumulator add and subtraction module. Now, the configuration of this DSP block is based on an instantiation that is available in the tools for iCE40 ULTRAPLUS, and you can either build a multiplier, multiply, accumulate, and or add, subtract only functions. The SRAM block, the hard IP in the SRAM block, is also consisted of 4 256-bit single port SRAMs. Each one of these blocks can be turned off individually, and each block has a sleep signal that can be controlled by the user logic in order to reduce power consumption. And the power off signal also can be controlled by the user logic to completely remove power from these blocks, hence reducing the power consumption for each one of these to 0. The SRAM can be configured as a 4-bit, 8-bit, 12, or 16-bit wide using some user logic, and they can all be cascaded to build a full 1 megabit SRAM block. As far as the SRAM is considered, this is different than the embedded block RAM available in this device. So there is both this 1 megabit of SRAM as well as some additional block RAMs available to be used. The RGB LED drivers in this family are 3 pins, dedicated pins, and behind each one of those pins is a 24 milliamp constant current sync driver, as well as a PWM generator for each one of these pins. So the pins can directly hook up to an RGB LED, and the PWM generators can be used independently to drive those RGB LEDs. And the outputs, these 3 outputs, can also be used as open drain outputs, standard open drain outputs, if the functionality of RGB LED is not required. So in that sense, you do not lose 3 pins because they are dedicated pins. We allow you to hook those up and make use of those 3 pins as open drain outputs. The IOs on ULTRAPLUS family do contain support for I3C IO. I3C is the new standard follow-on to I2C, and this is the new generation. And one of the benefits of I3C is the ability of removing the need for external pull-ups. So our devices offer, iCE40 ULTRAPLUS offers that function internally on IO pins. So all of the IO pins in iCE40 ULTRAPLUS are capable of having these various pull-ups individually programmed. So a 3.3K, 6.8K, and 10K ohm resistor can be programmed per IO pin for this I3C interface functionality. And then when this is used in high speed, the pull-up resistors can be dynamically switched off to save power when the pin is driving out. So that is a neat feature of this iCE40 ULTRAPLUS family. And each one of these pull-up resistors can be controlled separately, and they can keep the pin high when not driven. There is also a 100K ohm weak pull-up if the functionality of I3C is not required for every IO pin. And that can also be turned on or turned off at will. There are 2 oscillators, as I mentioned, in this product. There's a low frequency oscillator, 10 kilohertz, with the accuracy of plus minus 10%. And also there is a high frequency oscillator of 48 megahertz with the accuracy of plus minus 10%. The oscillators are very precise, but their accuracy is plus minus 10%. What that means is, depending on the silicon, from every silicon to the next silicon, there may be a variation of plus minus 10%. But once you turn on the device, each silicon will come up at a very precise frequency, and they will basically run at that frequency. For example, the 48 megahertz, one silicon may come up at 48 minus 10%, The next silicon may come up at 48 plus 10%, and the third one may come up at exactly 48 megahertz, but they will be running precisely at that frequency. And those can be turned off if not used to save power. And each one of these high frequency oscillators can be programmed at divide down modes of 24 megahertz, 12 megahertz, and 6 megahertz as well. The PLL available in this device does have a number of functionality and dividers. There is a reference clock divider in the front end. There is a VCO divider. There is a frequency divider. Also an optional 0 to 90 degrees phase shift capability. We do also offer some fine delay adjustment for the outputs. And we do have a low power mode as well to reduce power. A PLL, just like the oscillator, does consume some power. So for low power applications, if a PLL is not necessary, this should be turned off. We do have a slight power sequencing requirement for ULTRAPLUS devices during power up. We recommend that the VCC power and the VCC PLL power come up first. The second power supply should be the SPI VCC IO coming up, and then on the third and fourth stages, the VCC IOs and the VPP 2V5 pin should come up last. There is no order on the last section, but it is required that the VCC and the VCC PLL come up first, and then the SPI VCC IO come up second. And there is no time requirement as long as one follows the next. Could be a very fast operation. Typically, customers hook up the first power supply, the second power supply to the first one, and then the third to the output of the second, hence giving them this order. The I2C and SPI blocks, there is 2 I2C blocks and 2 SPI blocks available with very specific addresses, addressable from the external interfaces. We do have some optional 50 nanosecond delay hardware available for the iCE40 interface, as well as 50 nanosecond glitch filter for the clock portion of the I2C interface, and they can be used to make sure clean interfaces are applied to this device. For configuration modes, there is a SPI master and a SPI slave configuration mode available. This device can be only programmed through those 2 interfaces. The SPI master configuration mode does require an external SPI flash memory to hook up. So there are 4 dedicated pins on the device. There is a clock, SPI in and SPI out, and a chip select pin to be hooked up to the SPI flash memory. In the SPI slave mode, the device can be hooked up to a typical microcontroller or a microprocessor or an application processor through those same 4 pins. In this case, though, the clock direction changes and the direction of the SPI input and output change, hence enabling the iCE40 ULTRAPLUS to be driven by a microcontroller to be programmed. Both interfaces do run extremely fast, and the devices do program in only a couple of milliseconds. The MVCM programming memory and the SPI, the SRAM memory configuration space are accessed through the SPI controller. So everything can be programmed through this one interface. There is a self-download mode available when the non-volatile configuration memory is programmed, and that happens when the device is powered up. We do check for the MVCM memory to be programmed. If it is, we attempt to download the contents of that into the iCE40 ULTRAPLUS SRAM configuration space and through some configuration logic that's available in this device. If the device is configured through MVCM, that can be bypassed, as mentioned before, through the SPI interface. And the device can be reloaded through a SRAM, through a SPI interface using a microcontroller or our programming hardware. So we covered the different features and hard IPs of this device. As far as hardware is concerned, there is a 1 megabit of integrated SRAM, up to 8 16-bit multiplier accumulators. There is programmable IOs, hardened I2C and SPI interfaces, built-in oscillators, 5300 lookup tables, the 3 24 milliamp constant current sync RGB LED drivers, and the embedded non-volatile memory. All of these are the features of the iCE40 Ultra Plus. Here is the two members of the family. There is a 3000 lookup table and a 5000 lookup table device. The 3000 lookup table actually does have up to 2800 lookup tables. The 5K device has 5280 lookup tables. Both devices contain the MVCM. Both devices have a static power lower than 100 microamps. Both devices do contain some block RAM. In the case of 3K, 80K bits of block RAM. In the case of 5K, 120K bits of block RAM. Some additional memory bits are available, as mentioned before, called the SRAM, and that goes up to 1 megabits. There is 1 PLL per device. Remember, there's 2 I2C and 2 SPI cores, 1 10 kilohertz, 1 48 megahertz oscillator, 3 24 milliamp drive RGB pins for RGB LED functionality. And in the case of the 3000 lookup table device, we do have 4 DSP blocks. And in the case of 5K device, we do have 8 DSP blocks and some PWM functionality. The packages available in this family are as follows. There is a 30-pin, 49-pin wafer level chip scale package devices as small as 2.15 by 2.55 millimeters and the ball pitch of 0.4 millimeters. The 48 QFN package is a 7 by 7 millimeter package with a ball pitch of 0.5 millimeters. And the QFN packages do contains all of the pins on the circumference of the device, so much more easier to access and probe if needed for troubleshooting. This slide compares our Ultra Plus family with the other members of iCE40 family of devices, the iCE40 Ultra and the Ultra Lite. I'm not going to go through all of the features and details of the other families, but this shows where it stands compared to our various iCE40 family of devices. And all of these devices are available for in full production at the moment. All the packages are available, shipping to all of the customers across the world. One of the most popular family of devices for Lattice and the highest volume usage for Lattice Semiconductors.